Welcome back to this third part of our talk on understanding design of experiments. What we'll cover today will be the continued evaluation of the Capto S dynamic binding capacity data, now with an experimental design that supports the full complexity of linear terms, interaction terms, and second-degree curvature. We'll then also discuss a little bit around going beyond a DoE-only approach and how applying Monte Carlo simulation to DoE models can enable a probabilistic process design. So, reviewing again the application note data on the Capto S binding capacity optimization for the particular target protein that was evaluated there. We looked at how pH and load conductivity affected the dynamic binding capacity on the resin. This was performed by employing a full central composite phase-centered design, a design that supports linear terms, interaction terms, and second-degree curvature. In the previous part of the talk, we looked at how only looking at the corner points and the center points, so excluding the star points, worked in an evaluation, and it didn't work too well because we had clear evidence that we had a second-degree curvature. Now we'll move into using the whole data set, so including the star points. That's a design that will enable us to also quantify this curvature that we noted previously. So if we fit now this full RSM, response surface modeling polynomial, to our data, you'll see a dramatic increase in all the model statistics that we talked about on the previous example. The R2 value goes up to well over 90%, so our model fits very well to the experimental data. Removing the observations one by one or in a couple of groups, when it's this few experiments, it's most often removing experiments one by one. Removing them one by one and predicting them, truly predicting them, gives us a Q-square of around 80%. So it's an assessment, an estimation that around 80% of future variation would be possible to predict accurately by this polynomial model. The model validity also is very good. The model validity was the statistic coming from the ANOVA table that compares the residual variation to the overall replicate variation across the center points, or whatever experiments that have been replicated. In this case, it's the center points that we have replicated. So, and finally, the reproducibility is still very good. The center points have a low overall variation compared to the total variation across all experiments performed in the experimental design. So the ANOVA table, now for this polynomial model with the included square terms, performs drastically better than the previous only full factorial model did. So when we look at this middle part of the ANOVA table, that was when we compare the regression variation, how much is captured by the regression versus the residual variation. And now the regression number is wildly much bigger than the residual, the amount of variation sitting in the residuals, meaning that we get a very low and green p-value saying that it's extremely unlikely, this is the probability, it's extremely unlikely that the regression and residual aren't different, meaning it's extremely likely that they are different, which is a good thing in terms of building a regression model. We do want to capture the majority of the variation in our polynomial model and not have the majority of variation sitting in the residuals. So this tells us that we have a statistically significant R2 value, more or less. The bottom part of the ANOVA table compares, again, the residual variation to the replicated center point variation. And again, this is the opposite of how we would like the regression versus the residual to be. It's a case where we would like the two to be in agreement. We would like the lack of fit or the residual variation to be in agreement with the reproducibility variation in terms of magnitude. And in this data set for this polynomial model, we have that. So the model looks to be in good shape, and the residuals are in good agreement with the reproducibility variation across the center points. So it seems that we have a model that is sufficiently complex to accurately describe the process. We don't know if it's the optimal refined model. It could be that we have too many parameters in the model, but at least we know that it seems that we don't have too few at least. So next step now is going to be, again, to look into the residual variation and see if we have any systematic structures or variations or trends in the residuals. Remember, we would like the residual part, the error part, to only be random variation with no time trends and no structures versus anything. Starting out, same as previously, with the normal plot of the residuals. And here we get that, it's even a textbook example of how a residual plot would look if the data is normally distributed. We get an extremely nice straight line on the normal probability graph, indicating that whatever this model cannot predict is most likely random variation following a normal distribution, which is good news. If we graph the residual versus run order just to see if we have any strong trends over time or not, it seems that we do not. There's at least no immediately strong outliers. It's still not so many experiments that we would make any strong conclusions because this one is here and sort of ends up here. Overall, there is no big shifts or big trends. And also the evidence that the residuals are normally distributed is in favor of this not being over-interpreted as well. If we now look at the residuals versus the individual X variables, the pH and the load conductivity, if you recall from the previous part of the talk, that was where we had this strong curvature with a maximum in the middle, a curvature remaining in the residuals. This is now gone. Since we added the square terms to the polynomial captures the curvature, and the residuals just show some variation versus the pH. And if we look versus conductivity, it's again the same. No systematic structures or trends or shifts going on there. So very good news for the residuals. So far we can conclude that our model is doing a good job statistically. The R2 is significant, and we do not have a statistically significant lack of fit, following from the ANOVA table. We looked in detail at the residuals and saw that they were normally distributed, which is good. They did not have any time-dependent trends or shifts, and we see no structures or systematic trends also versus the individual X variables. So at this stage, we are now done with evaluating the error part. If we think about it, so far we only talked about the model as a whole and the residual part. Now it's turn to look into the f of x part and look for that. One could be tempted to dive too quickly into the f of x part, forgetting about making sure that the errors do not contain stuff that would tell us to make more experiments. Now that we can tick the box for the residuals, everything is well there, we'll move into looking at the f of x part. And in this case, that's actually going to be really quick. Starting out, one would look at the individual parameters in the polynomial and assess each of them for significance to see if all model parameters were statistically significant or not. So for this model we're looking at now, we have 5 parameters in the polynomial model plus a constant term. The 5 model parameters would be, starting from the left, the linear term for pH, which has an estimate this size, and then with a confidence interval around it like this. And yes, as you can see, this confidence interval does not cross the 0 line up here. So the assessment is, from a statistical perspective, that this pH coefficient is statistically significant on the 95% confidence level. These confidence intervals are 95% confidence intervals. So that the pH is statistically significant as a linear effect. Conductivity also statistically significant and a stronger effect than pH. We then have the pH quadratic effect, the square term, again significant, confidence interval not overlapping 0. Conductivity squared also significant, and interaction between pH and conductivity is also significant. Now it could be tempting to start to interpret how pH and conductivity are affecting the binding capacity from this graph. It can be done, but it's much easier done by other evaluation tools, which we'll come to. So now that we have successfully evaluated and verified that the model is sound from a statistical perspective, we will turn to interpreting the quantified effects, cause and effect relationships from within the DoE model that we've developed. So, of course, statistical significance is an important part of designer experiments. It's important from process development in general that whatever conclusions we make are based on really significant data. However, of course, it also is an important aspect that the transfer function, the model, the conclusions that we make about the process we're developing are sound and make sense from a mechanistical perspective. So, as I mentioned, we could try to interpret the effects also from the previous, the coefficient plot of the quantified transfer functions within the DoE model. However, within DoE we typically employ a couple of interpretation graphs or plots, simple graphs, to help us interpret what the cause and effect relationships within our process really looks like. Three classical typical ones are the interaction graphs, the main effect graphs, and the response surface plots. We will now have a look at each individual of those. So for the Capto S dynamic binding capacity DoE, we had, as you recall, a strong interaction effect between the pH and the salt during the load. So this is the interaction graph for how the effect from pH on the binding capacity depends on the setting for the conductivity. We should also take one moment here to mention about the resin that we're actually studying here. It's the Capto S resin, as we said. That's a cation exchange resin that has been grafted and to get an extended surface. So there are extenders on the surface of the beads to make the capacity higher and the mass transport quicker. And with those kinds of ion exchangers, and that's true both for GE and other resins, we observe a non-typical dynamic binding capacity behavior. So classically, for a non-grafted, non-surface extended ion exchanger, we would expect the lowest pH and the lowest conductivity to give us the highest binding capacity. But as you can see already on this graph here, that's not what we get. So we cannot quantify how good Capto S is or how high the binding capacity is by just running the low pH and the low conductivity. That's a large part why DoE has such a big value in this instance for binding capacity, is that we quantify the rather complex behavior between conductivity and pH for this ion exchanger, the Capto S. So if the conductivity is high, if we have a high conductivity, so a lot of charge in the solution, we're following then the blue line. When pH changes, we see, so pH changes from high to low means that the binding capacity is going to increase, which is what we would expect for any ion exchanger, any cation exchanger. However, if we have a low conductivity, so very, very little competing charges in the solution, you'll see that we are already at the maximum binding capacity here, and actually what's going to happen when the pH goes down even more, so the protein gets even more charged, is that we're actually going to get a lower binding capacity, which is non-typical, and that's due to the surface being extended with those grafted wavy arms to really improve mass transfer and binding capacity. So this is as would be expected for a surface extended cation exchanger like Capto S. So we know it's not going to be the low, the lowest pH, lowest conductivity that is the best. We know there's going to be a sweet spot somewhere a little bit higher on either pH or under conductivity. And we can quantify that by the DoE approach. So we can also turn the interaction plot the other way around, so we can peel the orange the other way and now look at interpreting how the effect from conductivity depends on which setting we choose for our pH. So the blue line here, the blue curve, shows the effect from conductivity on binding capacity at a high pH when the protein is not so strongly charged. And you can then see that it has a big effect, the amount of charge we have in the solution. So starting from a low conductivity, we really have the highest capacities, and then the more competing charge we introduce, the lower the binding capacity is going to be, which is totally as would be expected for any cation exchanger. However, if the pH is low, you see that the lowest conductivity isn't actually the best, highest binding capacity, but we actually have an increase to some kind of maximum here, and then it drops off as would be expected again. So that's the interaction tools. We can also look at the so-called main effects plots, which is sort of peeling the orange or slicing the DoE around the center point. So we see now, for instance, here how load pH affects the binding capacity at the center point setting in conductivity. And we can twist it the other way around, look at how conductivity affects the pH at, how conductivity affects the binding capacity at the center point setting on pH. Now, both of these main effect plots I would recommend using them only if we do not have pronounced interaction effects. In this case, we do have pronounced interaction effects. However, if we want to present them, we would present them together with the corresponding interaction graphs as well, to make sure we don't oversimplify the effect, because the effects from pH and conductivity really should not and cannot be totally separated due to this interaction effect between them. Finally, a very powerful interpretation tool is also offered by the two-dimensional response surface graphs, where we choose two of our x's. In this case, we only have two, the pH and the conductivity, and then we make a graph of the polynomial predictions from the transfer function across the whole two-dimensional window for these two parameters. Now, the nice thing about interpreting this is these graphs based on DoE is that with DoE we actually did experiments in the corners of this graph and in the center, and in addition also for the start point. So we have very good experimental foundation for making this graph and looking at it and making conclusions from it. One point about response surface graphs, though, is to always make sure to mention to the audience what the model uncertainty is when you look at this, because it looks so convincing, and I mean we see clearly where the best binding capacity is, and the best binding capacity truly is in the lower conductivities. So we would like to have the conductivity low and the pH probably not the lowest, but rather a little bit more high to have the best conductivity. So definitely this is the best area in terms of having a high binding capacity. What we do not have here is any information on the residual standard deviation or the magnitude of the prediction errors. So that needs to be taken into account presentation-wise and also conclusion-wise about this. But it's extremely helpful, an extremely helpful tool to quickly see and optimize where we should go with our process and where we should not go with our process. So now, that was all about design of experiments, and which was also the main topic of this. But I would also like to mention share with you a few slides about going beyond a DoE-only approach, which is to employ which can be to employ Monte Carlo simulation based on DoE-based transfer functions to assess our processes for robustness. So we have talked about design of experiments as an excellent process development tool. It really maximizes the amount of information that we get from the number of experiments we perform. And we do so by systematically placing experiments at the extreme corners of our investigated experimental space, really giving us a solid knowledge foundation for how our process inputs affect all of our process outputs, and also how they interact with each other in doing so. And in addition, we quantify the random variability, sort of the prediction errors that we have talked quite a bit about. So a lot of good stuff coming from DoE. One of the drawbacks or inherent limitations in the DoE and in the DoE polynomial is that the DoE models in themselves, they offer point estimates of process behavior. So in the pH conductivity example, if we set the pH at 5 and the conductivity is 10, we'll get a prediction from the DoE transfer function, the DoE model, of what is the expected binding capacity at this exact point. And we can look at different points and draw all these response surfaces, which is wonderful and great tools. But the polynomial approach with only using DoE can have difficulty, or does have difficulty, in describing how variation in multiple process inputs is going to translate into variation in multiple process outputs. This is where Monte Carlo simulation comes in as a very useful tool when combined with DoE. So by employing a Monte Carlo simulation to a verified and refined DoE model, one can assess how robust our process is, or the process, the unit operation in question is, to variation in the process inputs across the investigated experimental space. Because it's not necessarily so that my process is equally robust throughout the investigated space. If we think about it, if we are in a strong uphill slope on the response surface, or on the effect on our Y, anywhere variation we have on our process inputs is going to translate drastically across to the output side. If we compare that strong slope to something where the response has reached a plateau, so it's almost flat, well, then where variation on the input side is going to translate very much less into variation on the output side. This is a cartoon to illustrate how Monte Carlo simulation works in effect, and how we have employed it now on the Capto S dynamic binding capacity model to illustrate this. So what we do, we have in the red in the middle here, is we've taken out the transfer function of the model from the DoE evaluation step, including the residual variation. So the quantified size of random variation plus the f of x part, the model coefficient, the verified mechanistically interpreted transfer functions that seem to make sense. So we have the function in the middle there. What we do next is to assume or employ probability distributions for the process inputs. So that in this case would be the load pH and the load conductivity. So instead of choosing a set point, only a target, we will say, okay, we have a target and we have some variation around this. Now what the best assessment for that variation on the process input is going to be, naturally it's going to depend on your application and on your, if you're transferring it to manufacturing, it's going to depend on how well they can control the load pH or the load conductivity. So assuming relevant distributions for the process inputs is of course very important. How Monte Carlo works then is by randomly sampling from these distributions that we have on the process inputs. We sample individual points for the process inputs plus from the random variation, the residual variation. You take those points and you run them through the red box, the transfer function, to get 1 point estimate for the binding capacity. Then you repeat that. You go back to square one, sample once again from all the distributions for the inputs plus the random variation. You run that through the transfer function. You get a second point for the dynamic binding capacity in this example. You then repeat this maybe 100,000 times or more. With today's computers, 100,000 times simulation on a typical chromatography transfer function is made in a matter of seconds. So what we can do then, in effect, is to take the whole distributions and run them through the transfer function and get on the right-hand side here the probabilistic distribution for binding capacity. So to exemplify that, here is how that would look for the Capto S example, Capto S response surface that we looked at previously, with two different set points for salt and pH, or conductivity and pH. So we have the first target, I'll use the arrow here again. We have a set point here at around, well, at this setting here, with some variation room around it. So we have some normal distribution in pH around this point, and we have some variation on the conductivity around this point. So we more or less have set a control space or an operating space here within the purple square. And if we run those distributions plus the random variation on the residuals through the transfer function, we get a Monte Carlo estimate of the binding capacity that looks like this. Maybe it's too small to read, but you can see, well, it's around 100, if I remember correctly, in binding capacity here. And we have some variation width, which is really taking into account all the uncertainties that we so far are able to quantify. It's all the random variation in the experiments, it is realistic variations on the process inputs, and in effect that gives a rather quite good probabilistic estimate on how my response is going to change. You can then see if we consider the alternative set point. Now I've moved from this setting here up to more a sweet spot. It's a higher prediction for sure, which is exactly what would be expected from the response surface. Sorry, but also you can see that with the same variation on the process inputs, we are moving the binding capacity on average quite healthily upwards, but we are also making the process more robust to the variations in the pH and the conductivity. And this would have been quite difficult, or let's say that it's quite available to get this kind of information when employing a probabilistic method like Monte Carlo to a DoE transfer function, a DoE model. So with that, we reached the end of this three-part lecture on understanding design of experiments. We started out by introducing DoE and the rationale for DoE, talking about some key concepts in design of experiments, like the model, the transfer function, different complexities that we employ in DoE modeling, linear effects, two-way interaction effects, and second-degree curvature. We also discussed how all the experiments we run in a DoE are used to quantify not only the cause and effect relationships between our process inputs and outputs, but also are used to quantify the random variability or the uncertainty of our process performance. We then used a simple application note on binding capacity on Capto S, where a DoE was performed using load pH and load conductivity as input parameters, and looking at how binding capacity on Capto S depended on those two in-process inputs. We evaluated it first by looking only at the full factorial design results. So we forgot about the star points we had performed in the application work and only looked at it from a full factorial point of view. So with a DoE that would only support a linear model with two-way interaction between pH and salt. And we saw that complexity was not enough. We saw it in the residuals. So we always start out with evaluating the error part, the residual part looking to see if there's any structure or systematic variation left in the residuals, also see if we have any time-dependent trends and so on in the residuals, in the error part. We also evaluated the residuals for normality to see if whatever the model could not predict was following a normal distribution or not. And we saw that on the full factorial design, we had a systematic structure in the residuals. We had a strong curvature. So therefore, we didn't proceed with the evaluation of that data, but instead extended the design with the star points, 2 experiments for pH to enable to quantify if we have a curvature in pH, 2 experiments for salt to enable quantification of possible curvature effects from salt or conductivity. And indeed, we found significant curvature in both pH and salt. So when we evaluated that central composite phase-centered data, and looked firstly again at the residuals, we saw that the curvature had disappeared from the residuals. There were no longer any systematic trends in the prediction error in the residuals. We saw that the residuals also very nicely followed a normal distribution. So meaning that whatever we couldn't explain in the f of x part was more or less random noise, random variability on how binding capacity changes when you run repeated runs on the process. We then looked at interpreting the f of x part. Once the error part was okay, we looked at first off to assess all the model terms for significance, so making sure that whatever we maintain and keep in the model is significant from a statistical point of view. Also then after that moving into interpreting those effects to make sure that whatever we say is significant from a statistical perspective also makes sense and is significant from a domain perspective or mechanistic understanding knowledge perspective. And we employed interaction graphs, main effect graphs, and response surface tools to enable that evaluation and interpretation of the DoE model. And then finally we talked a little bit about going beyond the DoE-only approach. So design of experiments is wonderful in terms of quantifying the f of x part, using all the experiments to also quantify random variability. However, the DoE approach is deterministic. We make point predictions using the DoE polynomial, and DoE transfer functions alone run into a little bit of problem, or a little bit more of a problem, when it comes to the question of quantifying how variability in the process inputs is translated through the process or through the transfer function into variability on the process outputs. And this is where probabilistic approaches, such as applying Monte Carlo simulation to the DoE transfer functions, offer a very good addition to the DoE approach. So we take a big step by applying the DoE approach, and then by also leveraging Monte Carlo simulation or another probabilistic tool, we can take another step in improving our understanding of how our processes behave and work. And of course, from a process development and scale-up and manufacturing perspective, the question about how variation translates through the process is also highly valuable. We can really try to make our processes as robust as possible by optimizing where we choose to operate within our investigated space. So with that, I thank you so much for your attention over these 3 parts of the lecture, and wish you all the best in your QBD DoE endeavors going forward. Thank you so much.